This AP exam review video is going to cover all things linear regression. Our problem stem for this review is that Lydia and Bob are searching the internet to find information on air travel in the US. They found data on the number of commercial aircraft flying in the US during the years 1990 to 1998. The dates were recorded as years since 1990. For example, the year 1992 would be recorded as year 2. They fit a least squares regression line to the data, and the appropriate output and graphical displays are shown on the slide here. So first question, is a line an appropriate model to use for these data? So when we answer this question, we're going to be looking at the scatter plot and the residual plot. In the scatter plot, we want to see a line that's reasonably straight, which we have here. And in the residual plot, we want to see pretty much nothing at all, a bunch of scatter with no patterns or trends. So being both those things are true, we would say yes, the scatter plot shows a linear association between years since 1990 and the number of commercial aircraft, and the residual plot displays no noticeable trends or patterns. Next up, it asks us to identify and interpret the slope of the least squares regression line. Just a note, they might abbreviate least squares regression line as LSRL, and that's just talking about the equation of the line of best fit. So the slope is this number right here, and we would interpret it as for every additional year since 1990, the number of commercial aircraft is expected to increase by an average of 233.517. You need at least one of these terms. I always put both, hoping that you'll remember at least one. Identify and interpret the intercept. The intercept, actually, let's backtrack a bit. Everything on this line is about the slope. Okay, this is the explanatory variable, and we're predicting the number of commercial aircraft. The constant is the intercept. Everything on this line is about the intercept. This number right here is the actual intercept, and that's the value that we would get when we zero out this explanatory variable. So if we were to plug 0 in for the number of years, since it's being multiplied by the slope, these end up disappearing, and we get that y-intercept. So the y-intercept is that 2,939.93. When there have been 0 years since 1990, so in other words, in 1990, the predicted number of commercial aircraft is 2930.93. Okay, again, we need this word, or we need to note that that's the average amount that we would expect in that year. Part D is really just an algebra question. It's saying if each new aircraft costs the FAA an additional $1,000 in regulatory costs, how much are the costs increasing each year on average? Well, if the number of aircraft each year is increasing by that amount, the costs would be increasing by that amount times 1,000, or $233,517 per year on average. Make sure you write all your answers in context. Part E, what's the predicted number of commercial aircraft flying in 1992? For this one, we're going to write the equation of the line. So the equation of the line, we're predicting the aircraft. This should have a hat on it, which I forgot there. All predicted values should always have a hat to note that they're not actual values. The year actually is a real value. We're plugging in 2, indicating 1992. So we plug in the years since 1990, we plug in 2, we get 3406.964. That's the predicted number of commercial aircraft in 1992. And it's okay that that's a decimal because we're talking about a predicted number, which kind of serves as an average. And it's okay that it's not a whole number. Find and interpret the residual for the number of commercial aircraft in 1992. Circle this point on the residual plot. So since our explanatory variable is years since 1992, we are going to look for year 2. That would be 1992. And we're going to circle the point corresponding to year 2. That's the residual for that value, and it looks like it's about 40. We can also see it in the scatter plot. It's a little above the line of best fit, and the residual is telling us the distance from that point there, that blue point, to the line of best fit. So first we'll identify it by noting that it's approximately 40. It's good to write approximately in front of any value that's not calculated specifically or exactly. And then we're going to interpret it. So this indicates that there were 40 more commercial aircraft than predicted based on the year. Now part G, use the answers for the previous two questions to find the actual number of commercial aircraft flying in 1992. Circle this point on the scatter plot. We just talked about that one. It's this one right here. Okay, and we're going to use our last two answers. So here we noted that the residual is approximately 40. And on the previous question, we had found the predicted number of commercial aircraft flying as 3406.96. Residual is actual minus expected. So we'll plug in 40 for that residual. 3406.964 in for that expected value. And we're solving for the actual. Now, when we add this over and we get 3446.964, since the actual number of aircraft would be like the real world number of aircraft, this number can't be a decimal. We would want to round this to the closest value, 3447, and that's because we're talking about actual aircraft. Part H, add a point to the scatter plot that has high leverage. So a high leverage point is going to be far away from the rest of the points on the x-axis. So let's say this x-axis extended out to, say, I don't know, 20. Any point far away from the rest of the x values would have high leverage. Okay, so we could maybe put that would be high leverage. And even if it's in line with this, let's say up here, that point would have high leverage because it's a bit further away from the other ones. It doesn't matter that it's in line with it. It would still have high leverage. Now, this point on the right over here is also going to be an influential point. And that's because if we were to include that point, it's going to pull the line of best fit towards it. So instead of following the trend that's following right now, it would end up flattening out a bit. All right, this point would not be influential because it's really just in line with those other points. So if we remove it, the line of best fit largely stays the same. All right, so that said, on to the next part. Interpret the standard error of residuals, S, in the context of the problem. That's talking about this value right here as 33.43. And that's the average distance from the line of best fit of all these actual points. So the actual number of commercial aircraft varied from the number predicted from the line of best fit by an average of 33.43. It's kind of like a standard deviation interpretation, average distance from the mean for standard deviation, but in this case, it's average distance from the line of best fit. So that wraps up most of the information back from Unit 2. Now we're going to jump ahead to Unit 7, where we did some inference procedures on regressions. So we'll start by justifying the conditions to perform inference procedures on this regression analysis. So the acronym to check these conditions is LINE. We have L for linear, and that's just noting a scatter plot here. We see a linear association between years since 1990 and the number of commercial aircraft. Independent. If we have a random sample, these residuals would be independent because they were randomly selected. Doesn't note anything like that, so I'm just going to state that we're assuming these residuals are independent of one another. Nearly normal, we take a look at the dot plot. It might be a histogram, it might be a box plot. All right, we're looking for something some kind of display of the residuals that we can justify a nearly normal assumption. So because this dot plot isn't showing any skew or any obvious outliers, we're going to say that this condition is met. And then lastly, the E is for equal spread. And for this one, we're looking at that residual plot, and we're just looking for scatter with no trends or patterns. Now, if you're asked to calculate and interpret a 95% confidence interval for the slope, we are going to follow the acronym PANIC. So P, the parameter, let beta represent the true slope of the regression equation between the number of commercial aircraft and the number of years since 1990. A is for assumptions. We did this on the previous slide. N, name the method. Conditions are met, so we're going to create a linear regression T interval. The I is the actual interval. Now this problem we can't put into our calculator because we don't have the actual data, so we have to calculate this by hand. So we're going to start with our slope, the sample statistic, so the slope from our regression output there. We need a critical t-score based on 7 degrees of freedom. There were 9 values in our sample, and degrees of freedom for linear regression problems is n-2. And then standard error of the slope, we're looking on this slope line here, and we see standard deviation. It's going to be that number right there. That has already done the calculation S over radical N for us, which is typical for t-score problems. So we don't have to worry about that when we get that regression output. It's already calculated. All right, so another note, just while we're here, this value is called the point estimate. All right, if you're ever asked about a point estimate, it's just the result of the sample, whether it's the slope in this case, or a p-hat, or an x-bar. All right, this is the margin of error, right, which is that t-score times the standard error. All right, so the margin of error ends up as 10.207. We get an interval of 223.3 to 243.7. The C in PANIC is conclusion. We are 95% confident that the number of aircraft increases by between 223.31 and 243.72 for every additional year since 1990. I forgot the key phrase that I'm always hounding you guys to forget, which is that we need to note that this is an increase on average, okay? Or we need to know that this is a predicted increase. All right, so down here, it's another way we can write it. We are 95% confident that the true slope of the regression model between the number of aircraft and years since 1990 lies between 223.31 and 243.72. Okay, now with this wording, we actually don't need to note that it's on average because we're talking about slope. So slope in this case is going to be rise over run, all right? And we're saying that it's going to be in that range. Is there statistically convincing evidence that the number of aircraft is related to year? Explain. This is asking us to do a hypothesis test, so we're going to follow the acronym PHANTOMS. And we did most of these elements on the previous slide. So the parameter we already did, let beta represent the true slope. Hypotheses we haven't done, so our null hypothesis is going to be that beta equals 0. That's noting that there's no association between these two variables. And the alternative is that beta is not equal to 0. That denotes that there is an association. Okay, so in other words, if there is an association and beta isn't equal to 0, we have a slope that's going uphill or maybe downhill. If it's equal to 0, we just have a flat line. All right, imagine a scatter plot with a whole bunch of points just scattered all over the place, kind of like what we'd like to see in a residual plot. That would have a flat slope with a slope equals 0. Conditions are met. We're going to conduct a linear regression t-test. This t-score, the test statistic, comes right from the sample. This hypothesis test is about slope, so we're on the slope line of that equation there. The t-score is 54.11. With 7 degrees of freedom, again, that's because there were 9 points on our graph, and degrees of freedom for linear regression, n-2. Our p-value comes from right here on the table, or we could use t-CDF in our calculator. But regardless, with such a low p-value, we will reject the null hypothesis because that p-value is less than 5%, and find that there is sufficient evidence to suggest that there's an association between the number of aircraft and years since 1990. Is it reasonable to conclude that the increase in number of aircraft is caused by the increasing year. Explain. So causal conclusions can only be made when we have an experimental design with assigned treatments. We don't have that here. We have an observational study. Because of that, no, we can't conclude that the increasing year is causing that increase in the number of commercial aircraft. There could be a lurking variable that's affecting both of these things at the same time. As the final few topics in regression, we're going to jump to a different question thread. You were given the following cost to build a square deck for your house. Use re-expressed data to create a model that predicts the cost of the deck based on the width. So when it's talking about re-expressing data, re-expressing a scatter plot, we're working with a set of data that doesn't fit the model that we're trying to force it into. So what I mean by that is if we were to make a scatter plot of this data, we can see that we have a curved association. This is not linear. If we tried to force a linear equation to run through this line, right, we would start off with some residuals that were above the line of best fit. Then we have a whole bunch below it, like we see here, and then the last couple again would be above it. So this residual plot, just in case we couldn't see that curve in the scatter plot, that residual plot is telling us this is not an appropriate model to use. We can't use a linear regression here. So instead, we're going to re-express the data. We're going to change it. And when we want to re-express the data, I'm going to have you guys follow these 3 steps in this order. So first, we're going to try to take the square root of y. All right, so we're just going to square root all these values, put them in list 3 in your calculator, and then look at a scatter plot of list 1 and list 3. See if it looks linear, looks approximately straight. If that doesn't work, try taking the log of y, put that one in list 3 and do the same thing. If that doesn't work, try the inverse of y, 1 over y. It will probably be one of these things. It's possible it won't be, and there's a bunch of other things that we can try, but we could sink a lot of time into this FRQ if we keep looking. So I would say try these 3, pick the best one, even if it's not perfect. Even if you don't get credit for that first part, you can use your equations to get credit for the next parts. So when we do this one for this problem, we see that the association is pretty straight. The residual plot looks pretty good. So we're going to write that equation based on the re-expression. So in our calculator, these values are now different. All right, we've square rooted 150 through 2250, all right, and made a new list. We're going to run a regression on list 1 and that new list of square rooted values, list 3, and we get this regression equation. When we write this, we need to note how the data was transformed in the actual equation. So our equation came from a data set where we square rooted that y value. So when we write this equation, we're going to show it with that y hat being square rooted. It's also good practice to use the variable names instead of the variables x and y. So in this case, x is width, and the predicted variable is cost. So cost will have a hat on it. If you don't use variables in the equation, somewhere in the problem you need to note like x equals width, y equals predicted cost, etc. So now we're going to use this equation to predict the cost of building a 30 square foot deck. We're going to plug 30 into that equation, in for the width, and we get 95.0882. Just keep in mind that this equation is telling us the square root of the cost because we re-expressed our data, and now we have to unexpress it. So we have to get rid of that square root by squaring both sides, and that gives us our prediction of $9,041.77. Also, just a note, if we had re-expressed with log, this is something that's not used very often. To reverse that re-expression, we take each side and we put it as an exponent on the 10. So the 10 to the log power cancels out. We just have the y left. And then on this side, we would have 10 to the second power. Are you concerned at all with this prediction? Why? We should be, because this is very far outside of the range that was used in the data to make this regression model. This would be called extrapolating. We really want to plug in values in this range, or at least close to this range. The further we go out beyond that range, the more inaccurate our predictions are likely to be.